Well, where would we be in the Linux world if it wasn't for lwn.net giving us regular updates on what's happening? And where would we be without the magnificent work in the kernel page? Jonathan Corbett is responsible for both of those. He's also co-author of Linux device drivers and a member of the Linux Foundation Technical Advisory Board and a regular contributor to the kernel. And that's a lot more than a three-line diff. He is talking today on the kernel report, and I'm sure that on behalf of Linux Conference Australia 2012, you'll give him a very warm welcome. Jonathan Corbett.
All right, well, thanks a lot. Good morning, everybody. Nice to see you all here. This is the kernel report. Those of you who've seen it before know that I tend to review roughly a year's worth of kernel development with an eye towards the themes that we'll see in the future and where I think things will go from there. There's been a lot that's happened over the last year and a lot that's coming, with the result being I have about a 3-hour talk to fit into 40 minutes, so I'm going to go fast. Hold on. So, a year ago, where were we a year ago? Where were you? Come a long ways. We don't have to worry about keeping our feet dry anymore. But a lot has happened at that time. But actually before LCA, in the beginning of 2011, we saw the first kernel release of the year on the 4th, which was 2637, a big kernel development cycle with well over 11,000 change sets going into it, coming in from almost 1,300 different developers. So to try to put a feature list for a kernel like this, of course, is kind of silly, so you pick a few things. I picked out the first half of the virtual file system scalability patch set that went in there. Very deep, low-level surgery within the virtual file system layer, trying to get rid of lock contention, especially in the file name lookup path. So for certain kinds of workloads, especially if you're doing a lot of opening and closing of files, you could actually see performance improvements of up to about 30% coming from this one set of changes that went in 37 and 38. We got the block I/O bandwidth controller, something people wanted for a long time, to divide the bandwidth of a disk device between various groups of processes and put absolute limits on what they can use. Finally got support for the point-to-point tunneling protocol in the kernel. Finally got some basic parallel NFS protocol support in there. And we got a mechanism called wake-up sources, which is just a way of characterizing, abstracting out devices that can wake the system from a sleeping or suspended state. This can be thought of as part of the solution to the Android opportunistic suspend problem. There's actually a whole lot more to it than that. So that was 2637, again, beginning of the year. What have we done since then? Well, just a little bit. There have been 5 more kernel releases made since then, another one in the works at the moment, bringing in well over 56,000 changes went into the kernel since 2637. That doesn't actually count the 3.3 merge window, which is underway right now, so it's about 10,000 changes short. We had about 3,000 developers participating in the kernel over the last year, and 340 companies that we were able to identify all contributed core code to the kernel. I've put up slides like this before. I think we all understand by now that the kernel is a very big and very active and very healthy development process and development community, and things have just not slowed down in any way over the course of the last year. So, also in January, we got a complaint from a guy named Mike Waitchison. Mike is the head of the kernel group for Google's data centers. He makes the kernels that run on all those machines there. So he has a couple of machines he has to worry about keeping going, and he wants to automate things. And he was complaining that every time they do a major version bump on their kernel, various things in the logs change suddenly and it breaks all of their automation. They don't like that. So he's saying that print K is not really the right way to do automation to support logging the system. This brought back the long-standing complaint that in Linux we really don't have any kind of concept of structured logging. What we've got is this function called print K, and so you can put in anything you want, including, for example, the printer's on fire. Or if you go looking around, you can find all kinds of stuff. About the only rule is no profanity, not in invisible messages. And so it's flexible, but it's got a lot of problems because there's no structure to it. There's no consistency even between, say, the messages emitted by different devices of the same type. So you can't really abstract that out very easily. And things can change, as Mike noted, from one release to the next. So you never really know what's going to change. So it really messes you up if you're trying to do automated network management, trying to understand what's going on from the logging stream. It's hard for translators trying to translate our messaging into other languages. It's hard for documentation, and so on. Some of us, once upon a time, actually had a shelf like that in our office. That is the famous VMS manual set. One of those binders consisted of nothing but a listing of every message that the system would emit, and what that message meant and how you could respond to it, how you could fix whatever that message was complaining about. We have no such thing in Linux, and no real way to make such a thing at this point. A lot of people have tried to address this problem over the years. There have been a lot of initiatives put forward, and they all tend to kind of bog down because it's a hard problem, and because, quite frankly, kernel developers don't want to be bothered with maintaining a structured messaging thing. They just, I mean, it's a kind of fundamental laziness, to tell the honest truth of it. But what we've seen in the last year is a new attempt to address this thing in a form called the Journal. This was presented at the Kernel Summit in October. This is mostly a user space initiative, but it requires some kernel support. In particular, they want to decorate kernel messages coming out with a whole set of environmental information, including very clear descriptions of what devices might be involved and so on, to try to regularize and structurize the messages. And they want to attach a 128-bit unique identifier onto every kernel message, so that then automated systems can look up the message, for example, without having to try to apply regular expressions to the text and so on, and try to go somewhere with that. Suffice to say, this proposal is controversial, but the people involved, that's Lennart Pottering and Kai Seivers, tend to thrive on controversy. That's kind of what they want. So they're in their element, and don't seem to be planning to stop anytime soon. So we'll be hearing a lot more about this in the coming year, and maybe they will actually come up with a solution to this problem. We will see. All right, moving on, February. In February, we have a different sort of, not a complaint that came out, this is actually a compliment posted by Greg Kroll-Hartman, saying, I'd really like to compliment the folks at Raylink who have stopped just dumping big ugly drivers on the kernel community, and instead have started patching the upstream driver and trying to make the in-kernel code better. This, he said, shows a remarkable willingness to learn how to work with the community, and we want to encourage that. And this is a story that we see repeated over and over again. It's something we seem to have to go through with about every company. We have to teach them how to work with us, what actually works well with the Linux community. But one by one, we convince them that they actually need to work upstream and get their stuff there with a lot of good results. So this seems like as good a time as any to put up my traditional slide about where the code in the kernel came from over the course of the last year. It looks a lot the way it has for many years. The percentage of volunteers has actually dropped a little bit over time, down to just under 14%. It used to be closer to 20. One could say this is maybe a bad thing. The kernel is getting too complex. There aren't really any easy problems to solve anymore, and we're putting off the volunteers coming in. Or one could say, on the other hand, that anybody who shows any real ability to get code into the kernel tends not to stay a volunteer for very long, because people come chasing after them with job offers. So to be a volunteer, you have to really want to operate in that mode. So that could be a good thing. We see a lot of the same old companies that have been contributing for a long time. As I mentioned many times, we see companies that compete very strongly with each other in the economic area, that cooperate very well in this area. And in fact, even now in these days, when all these companies seem to be suing each other out in the real world, they still collaborate very well in this area. And we even have Microsoft as one of our top contributors for this last year. Something that, I don't know if we'll see that repeated, but it was kind of fun to watch. Another way of putting this, I did a little plot, and you don't really have to make a whole lot of sense out of this other than to say that this is plotting the percentage of kernel contribution from some of the top companies ever since 2620. And so you see, with a lot of noise, there's a lot of straight lines. There are companies that have been working with us consistently over this entire time. This is several years with the kernel development at this point. The thing that I want to point out is these lines here, right? These are TI and Samsung, which have somewhere around 2630-ish, something like that, a little bit before, decided to up their game, start putting more code in the kernel and working with us. This is something we're seeing a lot of in the mobile and embedded industry. So they're finally figuring out how to work with the kernel community and to make the kernel better for everybody involved. This is a trend I expect to see continue and even accelerate as these companies figure it out and as the importance of mobile Linux continues to grow. All right, one other company-related thing came out in February. This is sort of when people learned about Red Hat's policy of no longer releasing all the patches they apply to their enterprise kernels as individual patches. Instead, they just give you one big tarball. So you can't see the change logs. You can't see why they did what they did. This upset a lot of people. It kind of goes against the spirit of our community in various ways. It perhaps goes back to what Bruce was saying, in that Red Hat has to serve its commercial interests. And its commercial interests in this case include making things a little bit harder for its competitors out there. So it's kind of sad that the competitive aspect of the distribution industry have gotten that way, but that is the way it goes. Red Hat still remains, of course, our top corporate contributor to the kernel otherwise. Moving on to March. Had, of course, another kernel release in March. They come roughly every 80 days now, with one big exception in 2011. So 2.6.38 came out. There's a lot of stuff in there, but the two that I think are the most significant are the per session group scheduling patch. This is the famous 200-line kernel patch that turned into about an 800-line patch by the time it actually got merged, that made the group scheduling mechanism just work. So you could partition the available CPU time between different groups of processes, and within each group the processes compete among themselves and not with the rest of the system. It gives you much better desktop interactivity in some situations. It allows you much better control over how the available processor time in your system is used. A similar thing is the transparent huge pages mechanism. This allows the system to quietly substitute huge pages, very large sized pages supported by the hardware, into the address space of processes that are running without the need for any administrator intervention, without the need to mess around with huge TLBFS, without the need to change your applications, all of which you used to have to do to use huge pages on Linux. And it made it just work. And so you get something like a 3 or 4% speed up even on a kernel compile, which is about the most huge page hostile workload that you can think of. For other things, you can do even better than that. Using huge pages really does speed things up. It's a very nice feature. And again, we made it just work. That's the best way to get new features out to the world and have people actually using them, is to make them just work, so you don't have to dink around with them. We also had the other half of the virtual file system scalability patch set that I mentioned before. Transmit packet steering is network scalability stuff coming out of Google. And the hierarchical block I/O bandwidth controller, so you can use the full control group hierarchy with the bandwidth controller at this point. Other thing that happened just after this release came out, during the merge window, is that Linus got too many pull requests from too many ARM maintainers that conflicted with each other. And so in typical Linus style, he threw a temper tantrum and said, people need to get a grip, this is crazy, and he stopped pulling them. And a lot of stuff that was meant to go in for the ARM architecture in 2.6.39 did not actually get in there because Linus just got upset and refused to do it. And that was the beginning of the whole problem with what we call the ARM mess, or the ARM problem. So it's worth looking at the background here. The ARM architecture is very interesting, and there's kind of a specification for an architecture without a platform around it. So everybody does everything differently, and so the hardware varies wildly in amazing sorts of ways. ARM developers have tended to have what we call the embedded mindset. They work on their own little problem, their own sub-architecture, without necessarily thinking about making the kernel as a whole better, and without necessarily thinking about how it's going to be to maintain this in 5 or 10 years. And there hasn't really been a lot of high-level oversight over the ARM tree. So the result is we get lots of little subtrees for various sub-architectures, lots and lots of duplicated code, lots of cutting and pasting going on within the sub-architecture and so on. And it's a big ugly mess. We've had messes before. We cleaned them up. We've had them again. What's going on here in particular is, like I said before, we've been asking these vendors for years to contribute back to the kernel, and now they're actually doing it. What we actually have is a problem caused by our own success. It's what you might call a high-quality problem. We have all this stuff coming in, and we just have not developed the processes to actually manage it yet and to get it together. So there's now a whole lot of work going into cleaning that whole mess up. Adding the high-level oversight, there's a new ARM tree that funnels a lot of the system and chip stuff, for example, through there. A lot of cleanup work, consolidating duplicated code throughout the tree, actually trying to make the ARM tree smaller over time, even as the amount of hardware that it supports grows. And acceleration of the move towards the whole flattened device tree mechanism. A device tree is just a text file describing the actual architecture of a specific system. This has traditionally been done in this area with what's called a board file, which is actually a C source code file. We make various calls to declare the various devices in the system and where they live and how the whole thing is put together. But you can actually do that with a text file that's passed into the kernel by the bootloader. And that gets us closer to this holy grail of having one ARM kernel that can run on any ARM system. That's probably something we'll never achieve, but we can certainly get to where we have one kernel that runs on a whole lot of fairly modern ARM processors and so on, and that would be a very good thing. And we'll get there. We'll see a lot of work done on that over the course of the coming year. That's what April looks like in Utah. Nice place, but the network connectivity sucks, so you may not want to go there. In April, we saw the dreaded return of the native Linux KVM tool. This is a user space tool. It's a replacement for the QEMU hardware emulator, which is normally used with KVM in virtualization situations like that. This is meant to be really simple, very quick to make use of, aimed at kernel developers. The problem with this tool is not its existence, because nobody really objects to it, but the fact that they want to actually put this user space tool into the kernel source tree next to perf and a couple of other things that are there. And that started a whole big long fight. All right, there are people who will claim there are a lot of advantages to putting user space tools into the kernel source tree, including making the code a whole lot more visible. You work on it, becomes part of the kernel, you can work on it, you make a change, you end up in the kernel change log, all that sort of stuff. So you get more developers, right? It allows, they say, the development of the ABI and its users together, hopefully resulting in better ABIs from the kernel, and encourages developers to think across that kernel user space divide, which tends to be a very hard boundary for an awful lot of developers who will work on one side or the other, but not both. And they say it leads to better integration in the system as a whole. On the other hand, people will complain that it bloats the kernel tree, which is not small as it is now, that it can lead to ABI stability problems, because people who are working on an in-tree user space tool, if they break it with an ABI change, they just fix the tool and they go on and nobody notices anything. But the out-of-tree users then get broken by that. That's not supposed to happen, but there are people who claim that it does. They also claim that out-of-tree projects are disadvantaged with less mindshare, less developers, and less attention in the design of the ABIs, and they ask, where does it end? Do we throw our desktop environment into the kernel tree? Do we want LibreOffice there? So on and so forth. And this fight has gone on for a while. Various people posted things. Ingo Molnar, a fairly prominent kernel developer, says it's only a matter of time until somebody takes the kernel, throws in the C library and a user space and a tool chain, and makes this really nice, fully integrated distribution. Everybody's going to love it, and it's going to take off. Other people really disagree with it. Linus seems to be holding the line on pulling more stuff, user space stuff, into the tools directory at the moment. But I don't think this fight's going to go away. We'll be hearing a lot about this as we think about how to manage our source tree going forward. One other sad little quote. This came out at the Linux Foundation's Collaboration Summit, where Mark Charlebois from the Qualcomm Innovation Center got up and said, the mobile space is about proprietary drivers. Deal with it. That's life. It just sort of goes to show that no matter how long we try to convince vendors about the evils of proprietary and binary-only drivers, we have to convince everyone. We have to go through the whole fight over and over again with every single one. So we're dealing with this in the mobile area now. It's going to go on for quite a while, unfortunately. But we have pretty much always succeeded almost all the time in the past. I think we will this time too. Moving on to May. In May, we saw the posting of an interesting technology enhancing the secure computing mechanism that's in the kernel now. This is a developer named Will Drury who's working on the Chrome browser. And he wanted the ability to just add a bitmap into the kernel that would describe which system calls would be available to the calling process and which ones would not. Simply restrict the number of system calls available to the process that, say, is going to run a browser plugin, something like that. Reduce the attack surface, make better sandboxing. People said, okay, yeah, that's really cool, but maybe we could add various sorts of filtering schemes and maybe an kernel interpreter so that we could allow operations on, say, this file descriptor, but not that one, so forth. And maybe we could enhance the trace point mechanism to do all this stuff for us, but it was, oh no, you're not touching my trace points to do that kind of thing. And we ended up with a big fight, smoke visible for miles, and so on, and nothing got merged at all. It just sort of went away. So one could say that this is an example of the kernel process at its worst. Big fight, everybody has to get their 2 cents in, and then this promising young developer trying to actually get work done just gets discouraged and leaves. On the other hand, he just came back just last week with a new version of this patch that does things very differently, uses the Berkeley packet filter mechanism to load little programs into the kernel using an existing interpreter that's already there in the kernel and networking subsystem now, and seems to work very well. People seem to be very happy with it. He may actually succeed this time. So in fact, maybe what we're seeing is the best of the kernel development process, where second-rate solutions don't make it in, that even if we have to wait a little bit longer, we will push back until we get something that really satisfies all the constituencies and works for everybody. We will see. But that's where that's going. I bet we'll see that go into the kernel sometime this year. Of course, we had another kernel release in May, 2.639, relatively busy development cycle. Even if the headline features are relatively small, directed yield is an optimization for virtualized guests. IP set, a mechanism for dealing with large numbers of subnet numbers and so on, and firewall rules as part of the firewalling subsystem. Went in there. Transcendent memory is an interesting mechanism by which you take some of the system's memory and take it out of the kernel's direct view and use it, say, for caching compressed copies of pages or various other sorts of tricks that you can apply. If you search it out, you can find a lot of stuff on the net that's been written about it. Can't really talk about it here, but that went in 2639, at least the core of it. The users of it generally did not. User namespaces are part of the long-standing containers problem, trying to support containers running on the host kernel. This has been a multi-year project and is probably still a multi-year project. But user namespaces allow a certain amount of safe designation of privilege into containers without having to worry that they will corrupt the host system. And the media controller, which is a mechanism for configuring complex video acquisition devices. It's one of the many things we're seeing go in to deal with the complexity of modern hardware, because you don't just have a webcam device anymore. You've got a video acquisition device that may or may not filter the data through a lens distortion correction module, and the rotation and cropping module, and the scene detection and face detection module, and all that sort of stuff. And you end up kind of plugging all these wires in the hardware. So we're trying to add APIs to allow user space to do this in some sort of a reasonable way. And it's very complicated, and it's going to take a long time, I think, to figure out how best to do that. One other thing, in 2639, an unwelcome guest, we thought we'd never go, but we got rid of the big kernel lock. It only took us 15 years. But they never say that we lack for persistence in these things. Right after 2639 came out, Linus started pulling patches for what we thought was going to be the 2640 kernel. And he kind of has a weird day, and he says, I'm hearing voices in my head that says the version numbers are getting too big, so maybe I'll call this thing 2.8.0, which is what he was thinking at the time. Because when the voices tell him to do things, he listens. I want to be that voice. We started hearing other voices coming out after that, including Greg saying, hey, yeah, if you do this, I'll buy you a bottle of whiskey, whatever you want. So in fact, Linus did do it, decided that we would switch to 3.0. I think everybody knows at this point that the version number change didn't really highlight any significant change in the kernel itself. It's just that we got really tired of these big 2.6. Whatever version numbers. So we went on to 3. Whatever. So we did that, and in fact, in June, Greg bought Linus's bottle of whiskey, presented it to him on stage with cups. They did not participate, did not open it at that time, but that evening was kind of a mistake. Anyway, in June, we saw posting of a feature for the ext4 file system, snapshotting. A snapshot is just a capture of the state of the file system at a given time. You can use it for a lot of interesting things, like you snapshot the file system, apply a system update, and then you roll back to the snapshot if the update doesn't work. You can use it to make a backup of the file system in a quiet state, that sort of thing. So a useful feature. But people started asking questions because ext4 was supposed to be our stable stopgap file system. This is the thing that we run for now until we get ButterFS together and running with all the really cool new features. That's where that stuff was supposed to be done. So Joseph Basic, who is a ButterFS developer, asked, why are we cramming this stuff into our stable file system and destabilizing it instead of putting work into ButterFS where we can actually do these crazy things and not have to worry about it? So the truth of the matter is that ext4 is not quite the boring file system that people thought it was going to be. We've seen a lot of stuff going in. 3.2 saw the addition of BigAlloc, which is a fundamental change to the low-level block allocator. Rather than just allocating 4 kilobyte blocks, even for really huge files and file systems, it can now allocate blocks in larger units, like megabyte type units. It improves performance quite a bit on large files. People are quite happy with that, people who've benchmarked it and so on. So that went in for the 3.2 kernel. A whole lot of other stuff in the works, snapshots I mentioned, online resizing is sort of there, they're improving that, making it easier to work with, inline data for small files, optimization for very, very small files. Secure erase support, if you delete a file from the file system, it's actually physically overwritten and removed from the media. Checksumming of metadata to catch corruptions in the metadata, all that stuff. A lot of these things are well advanced. Some of them, the checksumming and the inline data, will probably go in for sure. The other ones are likely to. So ext4 is going to continue to evolve and develop for a while. It's not going to just sit there and wait until ButterFS kind of upstages it. Because, as Ted Cho said, people are finding that it actually works very well in a lot of situations. And there are many situations where the extra costs of the ButterFS approach, the copy-on-write approach, are just not a cost that you want to or have to pay. So we'll see a lot happening with ext4 in the coming year or two. Also in June, people started talking about this nifty thing called UEFI Secure Boot. This is a hardware mechanism that is meant to restrict the control of the hardware to trusted software. In particular, would only run the bootloader if that bootloader has been trusted by a key, or it has been signed by a key that is recognized by the hardware. So the idea is to thwart bootloader attacks and rootkits, that sort of thing, and ensure the system's running the software that you think it really is. This is actually, it can be a nice feature. It can be a feature that Linux users might want to make use of. There's just one little problem, which is the question of who is trusted. Is it the person who thinks they actually bought and own the computer? Foolish person they may be, or is it all these other people who think that they actually have a right to tell us how we're going to operate our systems? And all of these people would certainly like to have a say in what it is that we would run on our computers. So there's been a big fight over it, but what it comes down to is that this is one of these mechanisms by which we could lose control of what we think of as our computers. Right? We've seen many of those. This is the most recent one. There's been a lot of yelling has been done about this, a lot of work to call attention to the problem. And as a result, we've gotten a couple of concessions out of people at this point. One of which being that all x86 systems will have the ability to be put into what's called setup mode, where you can install your own key into the system. So you can not only boot Linux on the system, but you can actually boot it in the trusted mode if you want to do so. You can make use of that feature. But there are some problems with that. Installing that key may not be easy. This is a BIOS level operation. So we're going to be dealing with the user interface skills of BIOS developers to actually put that key in, which I mean may mean sitting down and typing in a very long hex number, which is going to be just a whole lot of fun. There's going to be no provision for booting from CD. This is not something they want to allow at this point, even with any kind of a user-present test. So live CDs may not work in the secure boot world at all. And I've put here that ARM systems can be totally locked down. The truth of the matter is, if they want to be certified for Windows 8, an ARM system must be totally locked down with no possibility for installing new keys into it. There's no way around it. If they want to certify that system for Windows, it must be locked down. This, people think, okay, well, this is the mobile handset world. Everybody's been doing that for a while. It's going to be really interesting if these fabled ARM servers actually ever show up. And when people start using ARM netbooks or whatever, it's going to go way beyond just the little mobile devices and so on. This is going to be a problem for real. We're going to have to continue to fight on that one for a while yet. All right, moving on, July. In July, we saw the first real-time patch set since March. Things had stalled for quite a while, leaving real-time users stuck on the 2.6.33 kernel, which wasn't really a whole lot of fun for them. But they finally got past some problems they had and put something out. The status of real-time at this point, it's been relatively quiet in a sense because for the most part it works. If you've got the right hardware, you can get very good determinism using the real-time patch set. They may have finally solved the per CPU data problem, which has been one of the thorniest problems with the real-time patch set thus far. The only problem is that it involves a lot of really scary assumptions about how locking is done in the kernel. And when we talk about scary in the area of assumptions about locking, we mean really scary. So it's going to take a while to verify all of that. But the plan is to merge much, or not all, but much of the real-time patch set in the course of the next year because they're really tired of maintaining it outside of the main line. So at the real-time summit that was held last October, they actually partitioned this stuff out and took assignments for fixing this stuff up and getting it into the main line. So we'll see it there. There's still a couple of open issues in real time, one of which is deadline scheduling. There have been patches out there for a while, but the developer working on that has gotten distracted with other stuff, so someone else may have to pick up deadline scheduling if we're actually going to get this feature into the kernel, which would be a really nice feature to have in the kernel. CPU isolation is the idea that you dedicate one or more processors to just the real-time task. No kernel work, no interrupt handling, nothing else. Nothing that gets in the way of your real-time work. There are various proposals out there for how we could do that. We may see some movement on that over the course of the next year. Beyond that, in July, we saw the delay of the 3.0 release to the point that it actually started pushing to Linus's vacation, which made him kind of grumpy. We had a nasty bug in the Dcache scalability work that I mentioned before. Every now and then a file would simply disappear for a little while and then come back. People find that disconcerting. So we had kind of an obscure debugging crew working on this stuff for the better part of a week. And it still took these guys, right? Linus, our main virtual file system developer, and arguably our main memory management developer. And it still took them several days to figure this problem out. It was a really nasty one. which highlights something that some of us have been saying for a while, which is that parts of the kernel have reached a level of complexity that is really scary. There are parts of the kernel that it's very hard to go in and understand what the invariants are, how things work, and how you can safely change things without creating weird little problems where once every few days a file disappears for a few minutes. I don't know how you fix that because the problem space is complex and not getting simpler. But it's something that we have to keep an eye on. Anyway, despite this, we did get the 3.0 kernel out towards the end of July. Some new POSIX clocks for waking the system from suspend, that sort of stuff. A just-in-time compiler for the Berkeley packet filter. We actually have a just-in-time compiler in the kernel now for a very restricted little language for writing these packet filters. The send multiple message system call scalability for messaging-oriented workloads. ICMP sockets are a way to write an unprivileged ping client, which some people wanted to do for many years. Namespace file descriptors are a mechanism for managing namespaces, managing containers, more of the container problem. And clean cache is part of this transcendent memory mechanism, sort of an opportunistic caching mechanism used in Zen in particular, in the virtualization area. So that's where we were in July. In August, the picture I took in Taipei, some aspects of hacker culture seem to be constant in any language, as far as I can tell. We saw a discussion in August about the x32 architecture. This sort of decloaked in the minds of a lot of people. x32 comes from the notion that we have to run our 64-bit systems in 64-bit modes because we simply want to address all of that memory in a rational way. Addressing anything more than a gigabyte or two of memory with a 32-bit system is possible, but not optimal. But the problem with 64-bit mode is that you bloat all your data out to 64 bits and all your pointers out to 64 bits, which means your program gets a whole lot bigger, which means it gets slower, even though it's very rare that you actually really need 64-bit pointers in an application, or that you need 64-bit data. So the idea behind x32 is that you run your system in the full 64-bit mode, but you use a subset of the instruction set so that you're always operating on 32-bit data, unless you've actually taken provisions to the contrary. So you get the best of both worlds. You shrink your data back down, you shrink your pointers back down, your program runs faster, that sort of thing. This is mostly user space stuff. They have to figure out the libraries and the tool chain and all that sort of stuff. But we have to get the system calls right between the kernel and user space to make this work. That was what was really kind of hashed out in August. And so and I think we'll see this push forward sometime this year. And at some point, we may actually see distributors starting to show some interest in shipping a version of the distribution that will run for the x32 ABI. In August, we celebrated 20 years of Linux since Linus first got out and said, I've got a tiny little project. So just the timeline I used in a plot at the time. The plot there is the size of the kernel in lines of code over time. So you can see a definite trend over the years. The kernel just never gets smaller, except for 2636, where we cleaned out a bunch of cruft and made it smaller. It's the only time, I believe, in the entire development history of the kernel that we've gotten the kernel smaller. And I don't expect to see that happen again anytime real soon. But 20 years of Linux, looking forward to the next 20 years. But what people really think about when they think about August, unfortunately, is the compromise of kernel.org, which was, this was not a good day. And at this point, what's known is that attackers had been on the system for some time before they were discovered, perhaps a really discouragingly long time. They got in using stolen credentials, then they somehow escalated to root. If anybody knows how that was done, they haven't told me. And they installed Trojan versions of the SSH client and server so that they could gather more credentials. As a result of this, the compromise spread way beyond kernel.org. And then one publicly known site, of course, is the Linux Foundation sites. But there were a number of developers who found their systems compromised and so on. It was not a good thing. But despite all of this, it's quite clear after a whole lot of investigation that no attempts were made to corrupt the software that's distributed by kernel.org. That's just not what these particular attackers were after. Perhaps, one could say perhaps they didn't know what they actually had. And that's a good thing. We would have caught them sooner or later if they had done that, but it's a really, really scary thought that you might distribute corrupted Trojan software to your users. You say, distribute bad make files to people who are running make inside their corporate firewalls and so on. It's really scary. And that did not happen, and that is a good thing. But kernel.org was down for almost 2 months. That delayed the 3.1 kernel release, and General stirred up our community quite a bit. So what's been done? We have a totally new kernel.org at this point. They basically threw it away, got a bunch of new hardware and started over again, built a new system with things much more better separated, hired some new staff to help manage it. It occurred to somebody that maybe having 450 shell accounts on the master machine was not the best of ideas. So access rules have been tightened considerably. At this point, there are no more shell accounts for all practical purposes. We built a new web of trust for the signing of pull requests and code going into the kernel, so we have a much better handle on the provenance of the code going into the kernel. And all this has been done with a lot of support from the Linux Foundation, which is taking a much more active role in the management of kernel.org going forward. So we hopefully have gotten a handle on this and solved this particular problem. But I've been saying this for years. I will continue to say this. We do not take the security problem anywhere near seriously enough. There are attackers out there who are capable and motivated, and they are not going away. And we are going to see things like this happening again. And I am not happy about it. I wish that we could do a better job of securing our systems and our processes. Moving on, September. In September, Oracle let slip on a development list that they actually plan to move to ButterFS by default for their enterprise Linux distribution. Sometime real soon now, not quite sure just when. So what's going on with ButterFS? Well, a lot of development work going on, but not a whole lot of feature work at this point because they're really focusing on stabilizing and getting to the point where they can declare this file system to be production ready. So that's where a lot of the effort's going in, and a lot of effort is going into that area. There are some open holes still. The main thing being the lack of a file system checker, or more to the point, a file system repair tool, which is a really hard problem to solve. So we don't have that. They've added a couple of stopgaps, including what's called the root block history array, which, since this is a copy on write file system, you can actually go into this history array, find the old root blocks, and get the older states of the file system for the recent past. So if you catch a corruption early, you just go into that array, regress the file system a little bit to before when the corruption happened, and life goes on. There's also a read-only data recovery tool that can try to extract data from a corrupted file system without actually trying to fix it, which always carries the risk that you break things worse than they were before. We're also missing the RAID 5 and 6 support. There are patches out there, have been out there for a while. Dave is ignoring me. They'll get put in at some point, I think. And then we'll have, I believe, our 4th RAID implementation in the kernel. You can never have too many of those, I guess. And ButterFS will come together over the course of the next year or so. October, everybody went to Prague. Of course, the kernel summit was there. We did our best to drink all of the beer in Prague, but I have to report that Prague has a lot of beer. And so we didn't succeed. So there's a lot of stuff that happened in the kernel summit. You can find it on LWN if you want. I just want to highlight 2 outcomes that came from it. One was this idea that maintainers should say no more often and not let so much stuff into the kernel. The other idea being that stuff should be merged, though, even if it's not up to our normal standards, if it is widely used out there, if it's been widely distributed and widely used. The target code in question here, of course, is the Android kernel code. That's what they're thinking about, but this can be applied well beyond that. If it's survived the test of time and is really being used, there's clearly value to it, and so we should go ahead and bring it into the kernel, even if we do not entirely like it. Also, during a slow moment, when Linus got bored, he went ahead and released the 3.1 kernel. This was a 95-day development cycle. This is the longest in many years. Again, this is the result of the kernel.org compromise. Various things in there, not a whole lot of really exciting stuff, but we added dynamic write-back throttling, trying to solve our write-back problems. Write-back, which is writing dirty pages back to their files on disk, has been a performance problem for some years now, and there's a lot that's been going on to try to fix that. We got a new architecture, which is open RISC, some improvements to the ptrace system call, try to make it safer and easier for applications to use, improvements to the LSEG system call, and various other things went into the 3.1 kernel released in October. Also in October, we saw the announcement of the Embedded Long-Term Support Initiative. This is an initiative put together by a group of embedded systems companies where they will pick a kernel once a year and support that for 2 years going forward. Use that as the basis for products in the embedded industry. Be a couple of other trees for their own stuff and for merging stuff back upstream. It's a determined effort from the embedded industry to work better with the kernel development community, and it is very much welcome. I hope it will succeed. Coming around to November. We saw a big discussion over a rather obscure technology called per C group TCP buffer limits. This is a control group-based mechanism to limit the amount of memory that can be dedicated to buffering TCP data for any given group of processes, network connections. It's the first attempt to limit the amount of memory that can be used by the kernel on behalf of user space processes. There's a lot of other efforts out there. We'll be seeing more of this stuff to come. There was a big fight over the impact on networking performance and so on. They overcame that, and this stuff will go in for 3.3. But it's part of the bigger control groups debate. Control groups, of course, are just a simple mechanism for grouping processes into hierarchies and applying policies to them. What people complain about, and what kernel developers complain about in particular, is the various controllers that are out there. There's a whole bunch of them controlling things like memory use, bandwidth, scheduling, and so on. They aren't always all that well integrated with each other or with the subsystems they control. Their overhead can be more than we want. So there's going to be a lot of cleanup work done in this area. What we really need is a control group maintainer. And so far, nobody has really stepped up to take that role. But someday, somebody's really going to have to, because we're accumulating a mess there in the core kernel, and that's not something we want to see. Something else that happened in November was the surprise pulling of the Linux Trace Toolkit Next Generation into the staging tree. LTTNG has been out there for many years as an out-of-tree development. It's widely used in some areas. Some people really like it. It's got some features that in-kernel tracing does not have. It was intended for merging into 3.3, and it ran into an immediate fight. So I want to put this slide back up. You've already seen this slide. On one side, we had people saying, we don't like this code at all. Maintainers are supposed to be saying no more often. We want to say no to this. Other people saying, well, but this is code that's widely used. People are using it. We should bring this into the kernel, and so on. Like I said, there was a big fight. And the outcome in this case was that LTTNG lost. Went back out of the staging tree. It's not going into the kernel for 3.3. And somehow those developers are going to have to find a way to integrate their work with what has been done in the kernel. We will see what will happen with that, and if they will come back, if they will simply maintain it out of tree from there. Coming around to the end of the year, that's what December looked like at my house. I suspect it looked a little bit different here. One thing to point out from December is the launching of the Android merging project. This is a formalized effort to get all this Android code into the kernel, various kernel subsystems that they have developed that we want to get merged. As soon as it was put out there, of course, people started arguing about it. We'll see how easy it will be to get that stuff into the kernel. A lot of it did go into the staging tree, though, so we'll see it at least that far, and we'll see what it takes to get it from there. And that brings us back around full circle to January again. I'm almost done. But we did, of course, have one more kernel release, exactly 1 year after 2.6.37 came out. We had the 3.2 release. This was a really big release at almost 12,000 change sets. Lots of stuff that went into this, including proportional rate reduction. This is improving the networking subsystem to recover better from packet loss. Extended verification module, more lovely trusted computing stuff that we supported in the kernel, defending the system against offline attacks, that sort of thing. CPU scheduler bandwidth controller, another control group controller. Cross-memory attach is an interesting inter-process communication mechanism that went in. Hexagon is a new DSP-based architecture that we support. The ButterFS recovery stuff that I mentioned before. And what's called IO-less dirty throttling, which is an interesting control loop-based mechanism for better controlling our write-back behavior, and especially the page dirtying behavior. Again, trying to improve our write-back behavior, and hopefully doing a fairly good job of it. It was a very interesting, very complex patch. All that stuff went in for 3.2 and more. We are actually in the merge window for the 3.3 kernel right now. So we don't have the full feature set yet. At least we hadn't when I last checked my mail. But we can see some of the stuff that will be in 3.3, including a new bonding device, lightweight bonding device for the networking layer, a new control group for arranging priority to access to the network interfaces, the TCP buffer size controller I mentioned before. Byte queue limits is a mechanism to limit the amount of data that can be queued for transmit out of any one network interface. This is an attack on the buffer bloat problem, and actually shows some real promise in fixing up a pretty severe problem that we have with networking net-wide. Open vSwitch is a virtual switch. Again, part of the networking subsystem used very much in the virtualization area. We also got large physical address extension support for the ARM architecture. You can now put more than 4 gigabytes of memory into a 32-bit ARM system if you've got the right kind of hardware to support it, and if you're actually crazy enough to want to do that. You can do so. The Android drivers return to the staging tree. DMA buffer sharing API is a mechanism for sharing memory buffers between widely disparate subsystems within the within the processor, for example, the video acquisition device and your graphics display device, moving data through the kernel in zero copy sort of mode. It's sort of addressing hardware complexity there. And this all will come out probably sometime in March if all goes according to schedule, and it usually does. And that's pretty much where I stopped. There's just all kinds of other things that happened over the last year that I could have talked about, but you would be here all afternoon and miss lunch and so on, and people would get grumpy with me. So I won't do that. I think maybe I have time for a question or two, if we have any.
Hi. Can you just explain how we got from 2.6 to 3.3 in only 12 months?
How we got from 2.6.37 to 3.3 be about 18 months of development time if you look at that whole series. The way the development process works now is it's pretty fast. It takes us typically about 80 days to create a new kernel. The average in recent years I think has actually been about 76 days. So we have spent about 2 weeks during what's called the merge window, cramming new features into the kernel. All right, that's what's happening right now for 3.3. And then we spend somewhere between 6, 8, 10 weeks stabilizing it. And we put it out there, and then it goes over into the stable tree maintenance and gets fixed up further from there, and we go on from there. But we have very much settled into a very fast process that's gotten a little bit faster over the years as we have gotten better at it. And it seems to be the best way to go. Nobody wants to go back to the older, slow release cycle that we used to have because it just took too long to get stuff out to users. Does that answer your question? You guys haven't been using your coffee tokens.
Okay, is this on? Okay, I know that a while ago, probably around 2.6.36, when Nouveau was introduced to the kernel, Linus said that a lot of the stuff that was entering the DRM tree was just untested crap, and then shortly thereafter that there were the ABI changes and everything else. Has that improved recently with the modern kernels?
Has the DRM tree and the graphics tree improved? I think most people would say that it has. I haven't seen a whole lot of big fusses. There's still complaints about how one vendor in particular is managing its contributions from time to time. But as a whole, it seems to be working pretty well. A lot of the worst problems have been solved at this point. We have kernel mode setting working. We have the memory managers working, and so on. So things are heading towards what you might call a very active maintenance mode at this point. Still a lot going on. But yeah, I mean, DRM was necessarily messy because it was a very hard problem to solve. We had to get a lot of work done. But that sort of stuff has been done. That's why we don't get Keith here telling us about what he's doing anymore, because they've pretty much slowed down with that. Just way back there in the middle. That's it. Faster!
I just wanted to ask a question about the transparent large page support. Is it completely architecture independent? If I run that kernel on an ARM machine which has multiple sizes, will I get the benefit?
Sorry, between the feedback and all that, I didn't hear that very well.
Is the transparent large page support completely architecture independent?
Is it architecture independent? It is primarily x86 at this point. I know people have been working on moving it to some of the other architectures, but I honestly don't have a handle on how far they've gone. But it has certainly been developed primarily on x86. There should be no real reason why other architectures wouldn't be able to support it very well, because most of the work was in the core memory management layer. So you need some architecture level glue to do it, and there's always going to be complexities. But I honestly don't know how far they have gotten in actually supporting that.
Okay, thank you.
Couple of quick graphics questions. First off, who do you think would win in a fight between the DRM developers and the frame buffer driver developers? And do you foresee any sort of fight coming on? And secondly, how many developers do you think would still be happier if DRM was decoupled from the kernel release cycle?
I'm not entirely sure I understand. The first part with regard to fighting between frame buffer developers and DRM developers, you know, they had a bit of a disagreement over how things should be handled a while back. And then it went quiet. But the simple fact of the matter is the DRM developers are active and developing the displays we actually use. The frame buffer subsystem is pretty much in fairly deep maintenance mode at this point. So in the end, if there is truly conflict there, the DRM developers are gonna win. The second part, were you simply asking about how many developers there are working in that area?
I'm just wondering, some graphics developers privately said that they'd be happier if DRM was pulled back out. Some graphics developers had previously said they'd be happier if DRM was possibly pulled back out of tree and developed. It wasn't developed as part of the Kernel release cycle, particularly for new hardware. How many developers do you think would be happier if that was going to be the case?
I haven't asked them that question. There was some grumbling again during the phase when they were really trying to nail down the memory managers and kernel mode setting and all that. They had real trouble with trying to do all this stuff without breaking the user space ABI, which is a real constraint that you have to deal with when you're dealing with in-kernel code. Again, I think we've gotten past the worst of that and they've figured that out. So I haven't heard a whole lot of complaints from that area. I mean, they may be complaining over beer somewhere where I'm not around. But I think it's working fairly well. I don't think there's a whole lot of trouble there at this point. And at this point, I think I definitely need to get out of the way and let Matthew do his talk. I thank you all very much for your time.
And Jonathan, on behalf of Linux Conference Australia 2012, we'd like to offer you a little gift for what you have done. Fantastic work. Thank you very much.